July 1st, 2025, and a team of astronomers at the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, are scanning the heavens as they do every night, hunting for anything unusual moving against that starry backdrop. Suddenly, their telescopes capture a faint, fuzzy dot streaking through the constellation of Sagittarius, near the bustling heart of our Milky Way. At first, it seems like just another speck of cosmic debris, but as the data pours in, the numbers tell a story that's anything but ordinary. This isn't some local wanderer from our solar system's asteroid belt or distant comet cloud. No, this is something far rarer, a visitor from beyond our sun's grasp, hurtling in on a path that screams origins from another star system entirely. They name it 3I divided by Atlas, the third confirmed interstellar object to grace our neighborhood, and as word spreads through the astronomical community, whispers begin. Could this be a messenger from the galaxy's distant past, carrying secrets older than Earth itself? Picture the excitement in those early hours. The ATLAS telescope in Rio Hurtado, Chile, flags the object at an apparent brightness that astronomers call magnitude 18, dim enough to hide from casual stargazers, but bright enough to intrigue the pros. It's moving fast, about 61 kilometers per second relative to our Sun, which is nearly twice the speed of previous interstellar guests like Oumuamua back in 2017, or Borisov in 2019. By July 2nd, observatories worldwide are turning their eyes toward it, confirming what the math already suggests: a hyperbolic orbit, meaning it's not bound by our Sun's gravity, it's just passing through. A cosmic hitchhiker that entered our system from the direction of Sagittarius and will exit toward Aquarius after swinging close to the Sunday. But here's where it gets truly captivating. Pre-discovery images dug up from archives, including those from the newly operational Vera-C Rubin Observatory, push the sightings back to June 14th, 2025. The Rubin, which captured its first light images on June 23rd that same year, had serendipitously snapped this intruder during its initial tests, revealing a slight growth in its hazy envelope, what we call a coma, hinting at icy gases waking up under the sun's warmth. As the days turn into weeks, more details emerge that make 3I divided by Atlas stand out, even among its rare interstellar kin. NASA's Hubble Space Telescope swings into action on July 21st, capturing a crisp image from 277 million miles away, showing a nucleus likely smaller than 5.6 kilometers across, wrapped in a glowing coma that's starting to sprout a tail. But the real puzzle comes from the James Webb Space Telescope's infrared scans in late summer. An unusually high ratio of carbon dioxide to water vapor in that coma, one of the highest ever measured in any comet. In our solar system's comets, water ice dominates, condensing at warmer distances from the sun, while carbon dioxide needs colder realms farther out. This skewed chemistry suggests 3I divided by Atlas, formed in the frigid outskirts of a distant planetary system, perhaps around a low-mass star where water never had much chance to accumulate. Or maybe, during its billion-year trek through the void, cosmic rays bombarded its surface, altering the ices in ways we've never seen up close. Adding to the intrigue, spectra from Chile's Very Large Telescope reveals strong nickel emissions but surprisingly weak iron signals, another departure from our local comet, where these metals mirror the sun's own makeup. Could this point to a birth in a stellar nursery with different elemental recipes, or some exotic processing in the deep freeze between stars? By early September, as the comet brightens toward naked-eye potential near the constellation Virgo, something even stranger unfolds in our skies. What starts as a routine month for astronomers turns into a celestial rush hour. On September 15th, a small near-Earth object dubbed 2025 RJ Two zips past at just 0.78 lunar distances, about 300,000 kilometers, close enough in space terms to feel like a brush with destiny. Then, just 3 days later, on September 18th, the headliner arrives. Asteroid 2025 FA22, a mountain-sized rock between 130 and 290 meters across, sweeping by at 2.2 lunar distances, or roughly 835,000 kilometers. Discovered back in March by the Pan-STARRS 2 telescope in Hawaii, this potentially hazardous asteroid clocks in at 10.8 kilometers per second, carrying kinetic energy equivalent to 100 megatons of TNT, enough to make headlines worldwide. NASA's Jet Propulsion Laboratory tracks it meticulously, confirming no threat. But the International Asteroid Warning Network uses the event as a live drill, coordinating global telescopes to measure its orbit, surface texture, and even albedo, that reflective quality that could affect future deflection efforts if needed. But 2025 FA22 doesn't travel alone. Throughout that same week, a parade of smaller visitors threads through our local space, 2025 BP6, skimming incredibly close, at just 9,710 kilometers from Earth's center, on some date earlier in the month, and others like 2025 QV5, on September 3rd, a bus-sized rock at 500,000 miles. It's as if the universe decided to throw a party in our backyard, with dozens of these ancient wanderers clustering in ways that defy easy explanation. Better surveys play a role the Vera C. Rubin Observatory, fresh from its first light triumph in June, nets thousands of new asteroid detections in its initial 10 hours of operation, revealing a busier solar system than we imagined. Yet the timing feels orchestrated, especially with the arrival of yet another spectacle. Comet C 2025 R2, better known as SWAN, discovered on September 11th by Ukrainian amateur astronomer Vladimir Bezugly through images from the Solar and Heliospheric Observatory's SWAN instrument. This comet bursts onto the scene with a greenish coma and a tail stretching 2.5 degrees, 5 times the moon's width, already visible in binoculars near the bright star Spica and the reddish glow of Mars in the western sky. After sunset, at magnitude 6.9 by mid-September, it's hovering on the edge of naked eye visibility under dark skies, its hydrogen-rich vapors lighting up as it races inward. Unlike the rocky solidity of asteroids, SWAN is a fragile, dirty snowball, its ices sublimating, turning straight from solid to gas under the sun's heat, creating jets that could unpredictably alter its path or even tear it apart. Perihelion hits just a day after discovery, on September 12th, at 0.5 astronomical units, half Earth's distance from the Sun, raising questions about its survival. If it holds together, we might witness a spectacular show, perhaps even a new meteor shower around October 5th, when Earth crosses its orbital plane, raining down fragments from this fresh visitor. Now, tie all this together, and you can't help but wonder, is this surge mere coincidence, or something more profound, stirring in our cosmic neighborhood? The Rubin Observatory's wide-field scans, capturing the ever-changing universe in unprecedented detail since its first images on June 23rd, suggest we're just getting better at spotting what's always been there. But with 3 I by Atlas's perfect timing perihelion on October 30th, hidden in solar glare until its grand re-emergence in early December, at 1.8 astronomical units from Earth, the patterns tease at deeper connections. Kinematic models hint this interstellar comet might hail from the galaxy's thick disk, a relic population of stars formed 7 to 12 billion years ago, making it older than our entire solar system. Ejected perhaps by gravitational tugs from giant planets in its birth system, it wandered the void, surviving cosmic ray blasts and stellar brushes. Like one 4 million years ago near a red dwarf in Cassiopeia, before arriving here, now, in 2025. If you're curled up listening to this podcast right now, maybe under a blanket in your living room at midnight in Seattle or dawn in Tokyo, hit that like button, subscribe for more cosmic tales, and drop a comment with your spot and time. It's like sending a postcard from your corner of the world, connecting us all under the same stars. Back to the mystery. As SWAM brightens toward potential binocular views in Virgo, and FA-22's flyby provides real-world practice for planetary defense, echoing the success of NASA's DART mission in 2022, which proved we can nudge asteroids off course. The questions mount. Why this clustering now, in September 2025? Observational bias from Rubin's quantum leap in sky coverage explains some, but the diversity rocky asteroids, volatile comets, and an alien interloper stretches probability. Speculation swirls. Could 3I divided by Atlas's passage subtly influence local debris, like a gravitational whisper herding smaller bodies? Physics says no, its mass is too slight at scales of millions of kilometers. But the idea lingers, fueling late-night debates among astronomers. Dig deeper. And the chemistry of 3I divided by Atlas adds layers of enigma. Its carbon dioxide dominance, captured by Webb's spectrographs, points to formation in a system richer in that gas, or farther from its parent star than our comets ever were. The nickel-iron imbalance suggests either exotic stellar abundances or billions of years of interstellar weathering, where high-energy particles from distant supernovas chipped away at its surface, creating isotopic oddities we might decode in December's prime viewing window. Meanwhile, Gemini Observatory images from early September show multiple tail components, each with different particle sizes and orientations, as if the comet is activating in phases, revealing hidden reservoirs of ancient volatiles. Episodic brightenings, independent of solar distance, hint at internal fractures, exposing fresh ices, cascading into dramatic flares that could make it a spectacle if it survives the sun's embrace. This interstellar arrival, combined with the September rush, awakens a sense of our solar system's true dynamism, not an isolated bubble, but a rest stop on the galactic highway, constantly visited by wanderers from afar. As Apophis looms in the background, set for its record-close pass in April 2029, closer than our geostationary satellites, visible to the naked eye. At 50,000 kilometers per hour, the surge feels like a prelude. Planetary defense experts, buoyed by DART's 32-minute orbital shift on Dimorphos, see these events as training grounds, closing blind spots like the sunward approach that hid Chelyabinsk in 2013. Yet the thrill lies in the unknown. If 3I divided by Atlas fragments at perihelion, we lose a pristine sample. If it endures, December brings our best shot at probing another star's debris, perhaps even organics, hinting at life's building blocks scattered across the galaxy. So, as we dive deeper into this cosmic drama, remember, the night sky above you tonight in 2025 is alive with these stories, waiting for your gaze. The surge isn't just data points, it's a reminder that we're part of something vast, where ancient travelers like 3I divided by Atlas bridge the voids between worlds, carrying echoes of creation itself. Stay with me as we unravel whether this is the galaxy's grand coincidence or the opening act of revelations yet to come. Shift your gaze to the pre-dawn hours of September 15th, 2025, when a tiny cosmic bullet named 2025 RJ2 sliced through the void, brushing past Earth at a mere 301,000 kilometers closer than the Moon's average orbit, a distance astronomers casually dub 0.78 lunar distances. This pint-sized rock, roughly 12 feet across or about the length of a small school bus, had been spotted just days earlier by vigilant telescopes, its path refined in real time by NASA's Jet Propulsion Laboratory. Hurtling at speeds that would make a jet fighter blush, it zipped by without fanfare, but not without leaving a ripple of quiet tension among those who watched the skies. No larger than a backyard shed, it posed no real threat had it struck. It might have burned up harmlessly in the atmosphere, like a spectacular fireball, but its stealthy arrival from the sunlit side of our planet echoed uncomfortable memories of past surprises, reminding us how easily these wanderers can sneak up unannounced. Barely had the dust settled from RJ2's flyby when the main event loomed. Asteroid 2025 FA22, a behemoth measuring between 130 and 290 meters wide. Think the height of a skyscraper, like New York's Chrysler Building tipped on its side. Discovered back in March by the Pan-STARRS 2 telescope atop Hawaii's Haleakala volcano, this space rock had spent months under scrutiny, its orbit mapped with pinpoint accuracy. On September 18th at 7:41 Universal Time Coordinated, or 9:41 Central European Summer Time, for those in Europe it swept past at 835,000 kilometers, a safe 2.2 lunar distances, traveling at 24,000 miles per hour. NASA's Center for Near-Earth Object Studies classified it as potentially hazardous due to its size and proximity, but refined calculations quickly dismissed any immediate danger. Still, the European Space Agency's risk list briefly featured it, a nod to the slim chance, once pegged at a remote possibility for 2089, that it might circle back someday. Thankfully, additional observations scrubbed that worry, turning the event into a valuable rehearsal for global coordination. What makes FA22's passage so intriguing isn't just its girth or speed, but the company it kept during that bustling September week. Picture our solar system as a vast, dimly lit highway, usually dotted with occasional traffic, but suddenly jammed like rush hour in a major city. Just before RJ2's cameo, another visitor, named 2025 BP6, had skimmed astonishingly close on an earlier date, clocking in at a mere 9,710 kilometers from Earth's center, barely grazing our planet's outer atmosphere if you factor in the radius. Then, hot on FA22's heels, came 2025 SY1 on September 19th, an airplane-sized chunk about 70 feet across, slipping by at 35,500 miles. These aren't isolated drifters. They're part of a swarm, with NASA's databases logging dozens of such close approaches that month alone. The Pan-STARRS surveys in Hawaii and the Catalina Sky Survey in Arizona contributed to the tally. But the real game-changer was the Vera C. Rubin Observatory in Chile, which unveiled its first light images on June 23, 2025, a milestone that flooded astronomers with thousands of new asteroid detections in just its initial 10 hours of operation. This flood of discoveries stems from Rubin's revolutionary design, an 8.4-meter mirror paired with the world's largest digital camera, capable of rescanning the entire visible sky every few nights. Those first images, released amid fanfare on June 23rd, showcased not just distant galaxies and nebulae, but a swarm of moving dots, asteroids previously hidden in the noise. By September, as Rubin's commissioning phase ramped up, it was spotting objects like FA22's smaller cousins with unprecedented sensitivity, revealing a solar system far more crowded than we thought. Is this surge a genuine uptick in activity, or are we simply lifting the veil on what's always been there? The latter seems likely, given how past surveys like Linear and Neowise missed fainter rocks. But the clustering in 2025 feels almost too convenient, sparking curiosity about underlying forces, gravitational resonances with Jupiter, perhaps, sinking these orbits over eons, or seasonal alignments as Earth plows through denser debris fields in its yearly loop around the Sunday. Delve into FA22's makeup, and the plot thickens. Radar pings from facilities like Goldstone in California painted it as a stony type, likely a carbonaceous chondrite rich in organics and water-bearing minerals. Remnants from the solar system's chaotic birth 4.6 billion years ago. Its albedo, or reflectivity, hovers around 0.15, meaning it's dark as coal, absorbing most sunlight and making it tricky to spot until close. During its flyby, amateur astronomers with modest telescopes caught glimpses as it peaked at magnitude 13.2 between September 18th and 22nd, a once-a-decade treat visible from dark sites. The Virtual Telescope project in Italy streamed the event live, showing the asteroid as a streaking point of light against fixed stars, its motion betraying the illusion of a static sky. Professional scopes, meanwhile, gathered spectra, hinting at surface weathering from solar wind and micrometeorites, layers that could tell tales of its long journey from the main asteroid belt between Mars and Jupiter. Compare this to the infamous Chelyabinsk event of February 15, 2013, when a 20-meter asteroid exploded over Russia with the force of 500 kilotons of TNT, injuring over 1,500 people, mostly from shattered glass. Dashcam videos from that day went viral, capturing a blinding flash and shockwave that rattled buildings like an earthquake. FA-22 dwarfs that intruder, packing energy 2,000 times Hiroshima's bomb if it ever struck enough for a regional catastrophe. Yet its safe passage offered a silver lining: real-time testing of alert systems. The European Space Agency's Near-Earth Object Coordination Center briefly elevated it on their risk list, then downgraded as more data poured in, exercising protocols for public communication without sparking panic. How do you tell the world about a skyscraper-sized rock hurtling nearby without headlines screaming doom? In this case, balanced reporting from outlets like Newsweek and Fox News emphasized the close but safe narrative, noting its energy equivalent to 100 megatons, while reassuring no impact loomed. This observational bias, the idea that better tools uncover more threats, explains much of the September buzz. Rubin's first light triumph on June 23rd wasn't just pretty pictures. It demonstrated a quantum leap in detection, netting asteroids in hours that older surveys might miss over weeks. By September, as the observatory fine-tuned its systems, it was cataloguing swarms like never before, turning what felt like a cosmic parade into a data deluge. But peel back the layers, and questions linger. Why did FA-22's trajectory align so neatly with RJ2 and SY1? Orbital mechanics offer clues many near-Earth objects hail from the Apollo group, crossing our path due to gravitational nudges from planets over millions of years. FA-22's modest eccentricity and inclination suggest a stable history, perhaps perturbed by Jupiter's mighty pull, herding it inward like a shepherd guiding sheep. Envision a three-dimensional simulation of these encounters, where Earth sits at the center, and trajectories arc like fireworks. RJ2 approaches from the sunward blind spot, that tricky corridor where daylight hides incoming rocks until the last moment. Much like Chelyabinsk's surprise entry, FA-22, by contrast, came from a more observable angle, allowing weeks of tracking. NASA's Scout system, an automated impact monitoring tool, crunched the numbers in real time, predicting its path with uncertainties shrinking from thousands to mere kilometers. This precision stems from international networks, telescopes in Chile, Hawaii, and Arizona, feeding data to the Minor Planet Center in Massachusetts, which disseminates alerts worldwide. During the flyby, even space-based assets like the Hubble chipped in, though primarily focused elsewhere, providing context on the asteroid's rotation, likely tumbling every few hours, a chaotic spin from ancient collisions. The human element adds depth to this celestial drama. Astronomers like those at the Lowell Observatory in Arizona, who contributed follow-up observations, describe the thrill of watching these ancient relics up-close fragments of the primordial disk that birthed our planets. FA22 might carry clues to life's origins, with carbonaceous materials potentially holding amino acids or water locked since the solar nebula cooled. If we could sample it, like NASA's OSIRIS-REx did with Bennu in 2020, we might unlock secrets of volatile delivery to early Earth. But for now, its flyby serves as a natural laboratory, with ground-based radars measuring its shape, perhaps elongated like a potato, common among rubble pile asteroids held loosely by gravity. As September's visitors fade into the distance, their echoes prompt reflection on our vulnerability and ingenuity. SY-1's airplane-sized bulk, passing at 35,500 miles on the 19th, underscores the diversity. Some are metallic ions, tough survivors from planetary cores, others fragile stones prone to breakup. This variety demands tailored defenses. Kinetic impacts work on solid bodies, but rubble piles might absorb the blow like a sponge. NASA's DART mission in 2022 proved the concept, shortening Dimorphos's orbit by 32 minutes, but scaling up for something like FA22 would require years of lead time. The surge highlights gaps, our sunward blind spot, where objects like Chelyabinsk lurk undetected until entry. Upcoming missions like NEO Surveyor, slated for launch in 2027 or 2028, aim to plug that hole with infrared eyes orbiting behind Earth, spotting heat signatures invisible from the ground. Yet amid the science, a tinge of wonder persists. What if this clustering hints at unseen rhythms, like debris streams from disintegrated comets or resonances amplifying encounters every few decades? Historical records show spikes think the Taurid swarm linked to Comet Encke, but 2025's feels amplified by our sharpened vision. Rubin's role can't be overstated. Its first light on June 23rd captured not just static beauty but dynamic motion, with algorithms sifting through petabytes of data to flag movers like BP6. This tiny interloper, at 9,710 kilometers, grazed geosynchronous orbit heights, where satellites dwell. A reminder that space isn't empty, but shared. Peering ahead, these events fuel curiosity about what's next. Will FA22's data refine models for future hazards or reveal mineral riches tempting asteroid miners? Companies like Astroforge eyes such rocks for platinum and water, turning threats into opportunities. But for stargazers, the real gift is perspective. In a universe of billions of stars, our planet dances amid constant flux, these flybys whispers from the deep past. As the month unfolds, with more visitors queuing, the sky invites us to ponder not with fear, but fascination, how these silent sentinels shape our story in the grand cosmic tapestry. The ethereal glow piercing the twilight on September 11th, 2025, when a Ukrainian amateur astronomer named Vladimir Bezugli sifted through fresh images from the Solar and Heliospheric Observatory's SWAN instrument, short for solar wind anisotropies, and spotted something extraordinary. There, amid the hydrogen emissions mapping the sun's invisible winds, bloomed an unexpected signature, a comet erupting with volatile gases, its brightness already rivaling distant stars. Officially dubbed C2025 R2 (Swan), this newcomer had stealthily approached from the sun's direction, explaining why ground-based telescopes missed it until now. Barely a day after discovery, it reached perihelion, its closest swing to the sun, on September 12th, at about 75 million kilometers, or half Earth's average distance from our star, unleashing a spectacular tail that stretched 5 degrees across the sky, 10 times the moon's apparent width. Bezugli's find wasn't luck alone. Swan, orbiting with SOHO since 1995, excels at detecting hydrogen-rich outgassing from comets long before they become visible optically. This one, emerging from the outer solar system's frigid reaches, carried the hallmarks of a fresh visitor. Pristine ices untouched by previous solar heat, now sublimating furiously into a greenish coma tinged by diatomic carbon and cyanogen molecules. By mid-September, observers in the southern hemisphere reported magnitudes between 6.5 and 7, faint but accessible with binoculars under dark skies, its tail a wispy arc, pointing away from the sun like a cosmic windsock. Photographs from astrophotographers like Gerald Riemann and Michael Jaeger captured the detail. A condensed nucleus wrapped in a hazy envelope, with the tail splitting into ion and dust components, the former bluish from solar wind interactions, the latter yellowish from reflected sunlight on ejected particles. What captivates about Swan isn't just its sudden appearance, but its fragile nature. A reminder of comets as cosmic time capsules teetering on the edge of destruction. Composed of loose aggregates, dust, rock, and frozen volatiles like water, carbon dioxide, and methane, these dirty snowballs form in the distant Oort cloud, a spherical shell extending up to a light year from the Sunday. Swan's orbit suggests a long period path, perhaps its first inner system venture in thousands or millions of years. As it neared perihelion, temperatures soared, triggering sublimation. Carbon dioxide jets at around 80 Kelvin, followed by water at 150 Kelvin, creating non-gravitational thrusts that tweak its trajectory unpredictably. Early predictions hinted at potential brightening to naked eye levels by October 19th or 20th during its closest Earth approach. But comets are fickle, many fragment under the stress, like the infamous Shoemaker-Levy 9 that shattered before slamming into Jupiter in 1994. Contrast Swan with Hale-Bopp, the great comet of 1997, which dazzled for 18 months, with a tail spanning 45 degrees and a coma brighter than Sirius. Hale-Bopp survived its solar encounter intact. Its massive nucleus, estimated at 40 kilometers wide, resisting thermal cracks. Swan, likely smaller at a few kilometers across, faces higher odds of breakup, especially as a fresh comet with volatile-rich layers. Recent cases, like C2025, F2 (Swan), discovered in March 2025, and disintegrating by May 1st, before its perihelion, underscore the peril. That one faded from view as internal pressures from rapid outgassing tore it apart, leaving a debris trail that might spark meteor showers years later. Will our September Swan meet a similar fate, or defy expectations with a surge in activity, perhaps producing outbursts like Comet Holmes in 2007, which brightened a millionfold overnight? For those eager to witness it firsthand, timing and location matter. In the northern hemisphere, catch it low in the western sky after sunset. Near Virgo's Spica and the ruddy dot of Mars, use apps like Stellarium for precise charts. Binoculars with 7x50 magnification reveal the coma as a fuzzy patch, while a small telescope might resolve the tail's structure. Southern observers in places like Australia or Chile have the edge, with the comet higher overhead in darker skies. Pre-dawn views work too, though twilight interference grows as it sinks toward the horizon. Amateur contributions are vital. Platforms like the Comet Observation Database welcome reports of brightness and morphology, helping refine models. Imagine Bazugli himself, poring over SOHO data from his home in Ukraine amid global uncertainties, his discovery a beacon of shared wonder, transcending borders as enthusiasts worldwide train their scopes on this fleeting guest. This vulnerability ties into broader cosmic puzzles. Why do some comets thrive while others crumble? The physics involve thermal gradients penetrating the nucleus, building gas pressure until crusts rupture, exposing fresh material in cascading events. Swan's greenish hue, from fluorescing gases under ultraviolet light, hints at organic compounds, perhaps precursors to life, delivered to early Earth via similar icy couriers. Studies of Comet 67P Churyumov-Gerasimenko by Europe's Rosetta mission in 2014 revealed amino acids and phosphorus, bolstering panspermia ideas where life's seeds hop between worlds. If SWAN holds such treasures, its potential disintegration could scatter them as meteoroids, some intersecting Earth's path around October 5th, igniting brief showers of swanids if fragments persist. Linking to the month's frenzy, SWAN's timing amplifies the intrigue without overshadowing the asteroids. While FA22 and its kin represent rocky resilience, this comet embodies ephemerality, its brightening coinciding with the surge, as if the solar system orchestrated a multifaceted show. Rubin's role here shines too. Though focused on asteroids, its wide-field scans caught SWAN's early motion, complementing SOHO's hydrogen maps. This synergy reveals a busier sky, where comets add volatility to the mix. Unpredictable orbits shifted by jets, unlike asteroids' steady paths. Long-period types like SWAN arrive with little warning, their hyperbolic hints suggesting Oort cloud origins, perturbed by passing stars or galactic tides over eons. Ponder the origins. The Oort cloud, a vast reservoir of trillions of icy bodies, envelops our system like a distant halo, seeded during the Sun's birth cluster 4.6 billion years ago. A gravitational nudge from a nearby star could have flung SWAN inward, its journey spanning light years in effective distance traveled. Spectroscopic data from ground observatories like Gemini show carbon monoxide and dioxide dominating early, outgassing, with water ramping up post-perihelion patterns, mirroring Borisov, the interstellar comet of 2019. But SWAN stays solar-bound. As it recedes, fading by late October, astronomers race to gather data. Hubble for high-res images, Webb for infrared chemistry, probing for exotic isotopes that might betray formation conditions. The curious builds. Could SWAN fragment spectacularly, creating multiple tails like Hyakutake in 1996, or persist as a binocular treat into November? Early reports from September 17th, via telescopic snapshots shared on platforms like Universe Today, show the tail elongating to 10 lunar diameters, a 5-degree streak rivaling the Milky Way's span in dark sites. If it brightens further during Earth's closest pass around October 20th, urban viewers might glimpse it unaided under pristine conditions, a rare gift in our light-polluted era. Yet, risks loom. Solar heating could trigger a total breakup, turning it into a diffuse cloud, as with C-2025F2 earlier this year. This comet's story weaves into humanity's gaze upward, from ancient omens to modern science. Babylonian tablets noted comets as harbingers, while today we decode their spectra for solar system history. SWAN's discovery by an amateur underscores accessibility. Anyone with internet can access SOHO images, potentially spotting the next one. As September wanes, with the comet dipping lower, the window narrows, urging prompt observation. Pair it with Mars nearby for a double treat, or track its evolution through apps updating ephemerides daily. Ultimately, Swan embodies the solar system's delicate balance. Ices forged in cold darkness, awakened by stellar fire, fleeting yet profound. Its passage amid 2025's asteroid cavalcade stirs questions. Does such clustering signal periodic influxes from the Oort cloud triggered by our orbit through galactic arms, or pure chance, amplified by tools like Rubin? As data accumulates, from brightness curves to tail dynamics, we edge closer to answers. Each observation a thread in the tapestry of cosmic evolution. Swan invites us to marvel at the Mongman, where beauty blooms from potential ruin, a luminous whisper from the outer dark. Focus to a cosmic veteran that's been lurking in the shadows of our collective imagination since its discovery. Back in 2004, a colossal rock officially tagged as 99942, Apophis, named after the ancient Egyptian god of chaos and destruction. This isn't some fleeting visitor like the September swarm we've been tracking. Apophis is a long-game player, a 400-meter wide behemoth that's spent decades orbiting in the inner solar system, occasionally dipping into paths that make astronomers sit up straight. Right now, as of September 21st, 2025, it's cruising through the constellation Virgo, a faint dot at magnitude 20.3, invisible to the naked eye, but steadily tracked by global networks. Its current distance? A comfortable 1.07 astronomical units from Earth, or about 160 million kilometers, far enough to pose no immediate fuss, but close enough in cosmic terms to keep it on everyone's radar. What draws us to Apophis isn't just its size equivalent to the Eiffel Tower laid flat, but its storied past as a planetary defense poster child. When first spotted by Roy Tucker, David Tholen, and Fabrizio Bernardi at Kitt Peak National Observatory on June 19, 2004, initial calculations sparked alarm. A potential Earth impact on April 13, 2029, with odds once pegged as high as 1 in 37. That sent ripples through the scientific community, landing it atop risk lists and inspiring doomsday headlines. But as more data rolled in, over 20,000 observations to date, refining its orbit to exquisite precision, the threat evaporated. No collision in 2029, nor in 2036 when it swings by again. Instead, what awaits is a spectacle. On that fateful Friday the 13th in 2029, Apophis will graze past at just 32,000 kilometers closer than our ring of geostationary satellites, orbiting at 36,000 kilometers, and visible to the naked eye for billions across Europe, Africa, and Western Asia. Imagine standing outside on that evening, gazing up as a bright point streaks across the sky at 50,000 kilometers per hour, brighter than magnitude -3, rivaling Venus on a clear night. No telescope needed. It'll move noticeably against the stars, a fast-moving star zipping from east to west in minutes. For skywatchers in places like Paris or Cairo, it could peak at magnitude 3.0. Easily spotted even from light-polluted cities. This isn't hyperbole. Simulations from the European Space Agency and NASA confirm the visibility, potentially reaching 2 billion people in the right hemispheres. It's a once-in-a-millennium event. The last time an asteroid this large came so close was likely thousands of years ago, before recorded history. But beyond the wow factor, Apophis offers a golden opportunity to probe how close encounters reshape space rocks, turning it into a natural lab for planetary science. Consider the gravitational tango it'll dance with Earth. At that proximity, Our planet's tidal forces, subtle stretches from uneven gravity, will tug at Apophis, potentially altering its spin rate, triggering surface landslides, or even redistributing its loose regolith, the dusty layer coating its exterior. Think of it like kneading dough. The asteroid that emerges post-flyby won't be the same as the one that approached. Pre-encounter data shows it's likely a rubble pile type, a loose collection of boulders held by weak gravity, similar to Bennu or Ryugu sampled by recent missions. Radar images from Arecibo, before its collapse in 2020, and Goldstone depict an elongated shape, perhaps peanut-like, rotating every 30 hours. But after 2029, that could speed up or slow down, with seismic shakes possibly exposing fresh subsurface material for spectroscopic peaks. This transformation is why space agencies are gearing up for close study. NASA's OSIRIS-APEX mission, formerly OSIRIS-REx, which snagged samples from Bennu in 2020, has been repurposed for a rendezvous with Apophis arriving in June 2029. Just weeks after the flyby, the spacecraft will orbit the asteroid for 18 months, mapping changes with cameras, spectrometers, and a laser altimeter, measuring how Earth's pull reshaped its surface and internals. Will we see fresh craters from dislodged boulders, altered spectral signatures revealing hidden minerals? These insights could rewrite models of asteroid evolution, showing how planetary brushes sculpt small bodies over geological time. Not to be outdone, the European Space Agency unveiled plans for Ramses in 2025, a rapid response mission inspired by NASA's DART, set to launch in 2028 and meet Apophis before the 2029 encounter. Ramses will shadow the asteroid through its Earth flyby, capturing real-time data on tidal effects with high-res cameras and instruments to sniff out any outgassing or debris ejection. Announced amid press briefings at the European Planetary Science Congress Division for Planetary Sciences joint meeting in September 2025, the mission highlights a shift toward agile spacecraft builds, using off-the-shelf tech to cut costs and timelines. Imagine Ramses as a cosmic chaperone, ensuring we document every twist in Apophis's path, while testing deflection, readiness for future threats. And with a budget around 200 million euros, it's a bargain compared to flagship probes, proving we can mobilize quickly against space hazards. Apophis's journey from villain to valuable asset mirrors our growing savvy in planetary defense. Early scares in 2004 pegged a 2.7% impact chance for 2029, but by 2006, better orbits dropped that to negligible. A brief blip in 2020 revived worries for 2068, but radar from Goldstone in March 2021 quashed it forever. No risk for at least a century. This evolution underscores the power of persistent observation. What started as a potential doomsayer became a benchmark for risk assessment tools like NASA's Sentry and ESA's NEODISE. Today, with over 95% of kilometer-plus asteroids catalogued, focus shifts to mid-sizes like Apophis, capable of regional devastation but detectable with current tech. Yet, the curious lingers. What lurks in Apophis's composition? Classified as an SQ-type asteroid from spectra, it's likely silicate-rich with metallic flecks, perhaps holding water-altered minerals, hinting at ancient hydration processes. If Ramses or OSIRIS-APEX detect volatiles, it could bolster theories of asteroids seeding Earth's oceans. And economically, with rare metals potentially worth trillions, Apophis tempts mining ventures. Companies like Astroforge eye similar rocks, though its speed and orbit make extraction a distant dream. Still, the 2029 flyby could inspire tech demos, like deploying CubeSats for proximity ops. Cultural echoes add flavor. Dubbed the god of chaos, Apophis inspired films like Don't Look Up in 2021, satirizing inaction on cosmic threats. Real-world parallels abound. Press conferences in September 2025 at EPSC-DPS emphasized Ramses as a practice run for deflection, building on DART's success. On September 8th, experts detailed the mission's timeline. By the 11th, they tied it to broader asteroid science. This buzz positions Apophis as a bridge between fear and fascination, a chaos god tamed by human ingenuity. Peering deeper, Apophis's orbit reveals solar system secrets. Its semi-major axis of 0.92 astronomical units crosses Earth's path, perturbed by resonances that once amplified close approaches. Post-2029, Earth's gravity will bend its trajectory, shifting future passes from mid-December to mid-September alignments, altering long-term predictions. Simulations suggest no threats until at least 2100, but vigilance remains. Key tools like the Vera C. Rubin Observatory, operational since 2025, will monitor for any surprises. For enthusiasts, tracking Apophis now offers practice. Apps like the Sky Live plot its position in Virgo as of September 21st, 2025, with a finder chart for 15 by 9 degree fields. Pair it with binoculars for a challenge at its dim glow. As 2029 nears, expect public events, live streams from observatories, apps simulating the flyby, even augmented reality overlays showing its streak. Apophis embodies the thrill of the unknown, once a harbinger of doom, now a teacher for tomorrow's defenses. Its safe passage will validate models, inspire missions, and perhaps reveal hidden facets of our cosmic kin. What changes will Earth's tug wrought? Will Ramses capture a seismic quake in action? These questions keep the wonder alive, turning a chaotic rock into a cornerstone of exploration. As we await 2029, Apophis whispers lessons in resilience, urging us to gaze outward with curiosity unquenched. Envision a serene morning on September 18th, 2025, shattered in an instant by the unthinkable. Asteroid 2025 FA22. Instead of gliding harmlessly past at 841,000 kilometers, as it did in reality, veers off its predicted path and plunges toward Earth. This skyscraper-sized intruder, estimated at 160 meters across by NASA's latest refinements, though some models push it to 290 meters, carries a kinetic punch equivalent to 100 megatons of TNT, dwarfing the 20 megaton Tsar bomber, humanity's most powerful nuclear test. At 10.8 kilometers per second, it slices through the atmosphere like a cosmic blade, compressing air into a plasma sheath hotter than the sun's surface. What unfolds next isn't Hollywood spectacle but raw physics, a cascade of devastation that could rewrite maps and lives in hours. The entry begins high, 100 kilometers up, where the asteroid starts glowing as friction strips away its outer layers. Traveling at 24,000 miles per hour, as reported in Fox News coverage leading up to the actual flyby, it would outpace any human-made vehicle, its leading edge reaching temperatures of several thousand degrees Celsius. For a stony body like FA22, likely a mix of silicates and organics, based on spectral data from observatories, it probably wouldn't reach the ground intact. Instead, atmospheric drag builds immense pressure, fracturing the rock mid-descent. Around 15 kilometers altitude, it erupts in an airburst, releasing energy in a blinding flash visible for hundreds of kilometers, like a second sun igniting the sky. Draw from the Impact Earth Simulator, a tool developed by Purdue University and Imperial College London. which models such scenarios with chilling accuracy. Input FA22's parameters: diameter 200 meters, density 2.6 grams per cubic centimeter, entry angle 45 degrees, and the results: paint apocalypse, a shockwave flattening forests and buildings across 2,000 square kilometers, akin to the 1908 Tunguska event, but amplified fivefold. In Tunguska, a smaller airburst leveled 80 million trees over Siberia's taiga. Here, overpressure waves exceeding 5 pounds per square inch would shatter windows up to 150 kilometers away, hurling glass shards like shrapnel. Thermal radiation lasts seconds, causing third-degree burns to exposed skin at 100 kilometers, igniting clothing and vegetation in a ring of fire. Imagine standing 200 kilometers distant. First, the light sears your retinas. Then a thunderous boom arrives minutes later, rattling the ground like a magnitude 6 earthquake. But what if the asteroid's composition skews denser? Say, an iron-nickel mix from a shattered planetary core. Simulations shift dramatically, punching deeper before fragmenting. It slams into the surface at 10 kilometers per second, excavating a crater 3 kilometers wide and 500 meters deep. Using Impact Earth's crater module, the immediate vaporization ejects millions of tons of superheated rock on ballistic arcs, raining molten debris across thousands of square kilometers. The seismic jolt registers as magnitude 6.5, triggering landslides and collapsing structures hundreds of kilometers out. Ejecta clouds the atmosphere, dimming sunlight regionally for days, while localized fires merge into infernos if it strikes dry forests. Now ponder the ocean scenario. Statistically likeliest, since 70% of Earth is water. A mid-Atlantic impact, for instance, displaces water violently, generating a tsunami with initial waves towering 100 meters at the site. Hydrocode models from researchers at Los Alamos National Laboratory suggest these propagate at jet speeds 500 kilometers per hour across basins. By the time they reach coasts, attenuation reduces heights to 10 meters. But that's still catastrophic. Coastal cities from Boston to Barcelona face inundation hours later, with waves surging inland up to 5 kilometers in low-lying areas. Factor in bathymetry. Seafloor contours and outcomes vary. Shallow shelves amplify waves, while deep trenches dampen them. A strike near the Puerto Rico Trench might funnel energy toward the U.S. East Coast, flooding New York harbors and washing away barrier islands. Human elements amplify the horror. Suppose it targets the North Atlantic. Shipping lanes disrupted. Transatlantic flights grounded amid ash clouds. Evacuation Keach ban unfold chaotically. Warnings from NASA's Planetary Defense Coordination Office, issued days ahead if detected early, trigger mass exoduses from coastal zones. But, with lead time potentially short, as in Chelyabinsk's zero-warning blast in 2013, panic ensues. Hospitals overflow with burn victims and crush injuries. Power grids fail from electromagnetic pulses induced by the plasma sheath. Economic toll. Trillions in damages. Supply chains crippled if ports like Rotterdam or New York vanish under waves. Newsweek's pre-flyby article on September 16, 2025, dubbed it a skyscraper-sized asteroid at 520 feet, emphasizing the close shave at 523,000 miles, 2 lunar distances, but hinting at what-ifs with expert quotes on impact risks. Fox News echoed the drama, noting its 24,000 miles per hour speed and up to 951 feet span, framing it as a massive asteroid bigger than a skyscraper zipping past, while underscoring NASA's assurance of safety. These reports fueled public intrigue, with social media buzzing about doomsday preps. But in our hypothetical, they become harbingers. Rescue operations mobilize. Red Cross deploys floating hospitals for tsunami survivors, while FEMA coordinates airlifts from rubble zones. Yet recovery drags radiation from vaporized rock? Minimal, unlike nukes, but dust veils could chill climates regionally, echoing the 1810 Tambora eruption's year without summer. Physics details intrigue further. Entry angle matters. A steep plunge maximizes penetration. Shallow grazes skim the atmosphere, potentially skipping like a stone before exploding. FA-22's actual trajectory was 45 degrees moderate, but tweak it 10 degrees, and outcomes flip. Composition plays too. If rubble pile, it disintegrates high, spreading blasts. Monolithic iron endures, cratering deep. Models from the University of Arizona's Lunar and Planetary Lab suggest FA-22 leans rubble, based on its low density inferred from brightness fluctuations during the flyby. Scale the terror. Chelyabinsk at 20 meters, injured 1,500. Tunguska, 50 meters. Flattened 2,000 square kilometers uninhabited. FA-22, 10 times larger, scales energy by 1,000 regional extinction. Millions affected if urban. A land strike over Europe. Paris or Berlin leveled. Shockwaves toppling the Eiffel Tower or Brandenburg Gate. Ocean hit. Tsunamis swamp. Lisbon. Dublin waves eroding cliffs. Salting farmlands. Environmental fallout. Aerosols lofted high could linger months, cooling by 1 degree Celsius, disrupting crops globally. Yet curiosity tempers dread. What lessons emerge? Impact Earth runs, show deflection, viability, spot it years ahead. A dart-like nudge suffices, but late detection, like sunward approaches, leaves mere evacuation. FA-22's safe pass tested systems. ESA's animation on September 16th visualized the flyby, educating on scales. In our what if, it underscores urgency. Invest in Neo Surveyor for infrared hunts, closing blind spots, ponder survival odds. Airburst spares craters but maximizes blasts. Ground impacts localize but eject more dust. Human ingenuity shines in aftermath. Drones map ruins. AI predicts wave paths. But the ultimate curious, could FA-22 harbor fossils or organics scattered in debris? Bennu samples showed carbon, an impact might seed biology ironically. This scenario, rooted in real data from 2025's event, blends terror with wonder, physics dictating fate, humanity adapting. What hidden variables tip the scales? Density unknowns, angle variances. Each simulation tweaks outcomes, keeping the cosmos endlessly unpredictable. As we reflect on the actual miss, gratitude mixes with vigilance, for space holds more such wanderers, waiting their turn. Peer into the spectral fingerprints, unveiled by the James Webb Space Telescope in late August 2025. And you'll uncover a composition that defies the norms of our solar system's icy wanderers. Interstellar Comet 3, I divided by Atlas, boasts one of the highest carbon dioxide to water ratios ever recorded, with CO2 dominating its gaseous halo in proportions up to 150% more than typical comets at similar solar distances. This revelation, drawn from Webb's infrared spectrographs, paints 3 I divided by Atlas, not as a run-of-the-mill visitor, but as a relic forged in an alien cradle, where conditions favored carbon-rich ices over the water-heavy blends we're accustomed to. Discovered on July 1st by the Atlas survey in Chile, this third confirmed interstellar object, following Oumuamua in 2017 and Borisov in 2019, has since revealed a chemical profile that whispers of distant stellar nurseries, potentially billions of years old, offering a tantalizing glimpse into the galaxy's formative epochs. Contrast this with Borisov, the second interstellar comet, whose coma showed carbon monoxide levels 9 to 26 times higher than average solar system comets, as observed by the Atacama Large Millimeter divided by Submillimeter Array in 2020. Borisov's CO abundance, estimated between 9 and 26% of its total volatiles, suggested formation in a system abundant in carbon monoxide ice, present only in the coldest reaches beyond where water condenses. Similarly, 3I divided by Atlas's CO, two dominance mixing ratios among the highest on record, implies it condensed far from its parent star in zones below 78 Kelvin, where carbon dioxide freezes while water remains gaseous. This skewed volatile balance, detailed in Fox Weather's August 27th report, challenges models of planetary formation, hinting at a birth around a low-mass star or in an extended disk where water ice was scarce. Adding layers to the enigma, observations from Chile's Very Large Telescope in early September detected prominent nickel emission lines alongside faint iron signals, a ratio inverted from solar system norms, where iron and nickel mirror stellar abundances. In typical comets like Hale-Bopp or Hyakutake, these metals appear in solar proportions, reflecting the primordial nebula's mix. But 3I divided by Atlas's nickel surplus, as noted by Smithsonian on August 28th, suggests either selective depletion of iron during its interstellar voyage, perhaps via cosmic ray spallation, breaking bonds over eons, or origins in a stellar environment with atypical heavy element ratios. This could point to the galaxy's thick disk, a stellar population 7 to 12 billion years old, where metallicity differs from our thin disk's sun-like stars. The comet's green glow, first reported in Science Alert on September 20th, adds visual intrigue, a fluorescence not fully explained by common emitters like cyanogen or diatomic carbon, despite their presence. Unlike Borisov's cyanogen detections at Lowell Observatory in September 2019, which aligned with solar comets, 3I divided by Atlas's hue persists even as it approaches perihelion on October 30th, suggesting exotic molecules or dust interactions under solar ultraviolet. X-posts from September 21st buzz with speculation. One user links it to doomsday comets from 12,800 years ago, while another questions artificial origins, echoing Oumuamua debates. Size estimates from Hubble on July 21st cap the nucleus at under 5.6 kilometers, likely smaller, placing it between typical comet cores and modest asteroids. Yet, its tail, imaged by Gemini Observatory, shows multiple components. Ion tails blue from charged gases, dust tails yellow from scattered light, orienting differently, indicating phased activation of volatile pockets. This complexity, as per Nature's September 17th article, reveals gases spewing months before official discovery, with pre-detection images from Vera C, Rubin Observatory's first light on June 23rd. Capturing early activity, Rubin's wide field prowess, netting thousands of asteroids in 10 hours, inadvertently flagged 3I divided by Atlas's coma growth, underscoring how new tech unveils hidden dynamics, episodic brightenings, independent of solar distance. Intrigue further. Unlike predictable curves of solar comets, 3I divided by Atlas flares suggest internal ruptures, exposing pristine ices, akin to Holmes's million-fold outburst in 2007. Polarimetry from ground scopes reveals unusual dust grains, possibly modified by interstellar radiation, creating optical properties unseen locally. This ties to Borisov's CO-rich profile, where abundances reached 173% relative to water, implying formation in CO-dominated zones. What does this mean for galactic history? If 3I divided by Atlas hails from the thick disk, its chemistry preserves snapshots of early Milky Way conditions. Higher star formation, different element distributions. Nickel-iron imbalance might reflect halo stars' low metallicity. Where iron synthesis lagged, organics, if present like Borisov's cyanogen, could hint at panspermia life's ingredients hopping stars. YouTube updates from August 22nd describe its bizarre tale, fueling questions. Is this natural variation or evidence of unseen processes? Perihelion hides it in solar glare until December. At 1.8 astronomical units, prime for detailed scans. Will fragmentation reveal deeper layers, or survival preserve ancient secrets? Rubin's first imagery on June 23rd, showcasing millions of galaxies and asteroids, sets the stage for such probes. X discussions speculate green glow ties to nickel, but cyanogen usually dominates. Perhaps exotic chemistry fluoresces uniquely. This comet's profile, with CO2 highs and metal oddities, opens windows to diverse planetary systems. Borisov's CO suggested birth near a red dwarf. 3I divided by Atlas might echo that, or thick disk extremes. Rotational anomalies, long periods, or tumbling from interstellar torques add puzzles. As data from Webb and VLT accumulates, each spectrum teases origins. Was it ejected by giant planets in a chaotic disk, wandering since before our sun ignited? National's September 19th piece notes surprising chemistry, offering insights into distant planets, abundant nickel, scant iron, perhaps from differential sublimation. Live Science echoes Webb's findings. CO2 divided by H2O ratios stretch limits, implying frigid birth zones. X users ponder artificiality, but natural explanations prevail. Cosmic rays altering surfaces over gigayears. Rubin's role in early detections, from June 23rd's swarm of asteroids, amplifies this. Thousands spotted in hours, including 3I divided by Atlas precursors. This chemistry bridges eras. From galaxy's youth to now, each volatile a clue to stellar alchemy variations. What if organics abound, like Borisov's hints? Panspermia gains traction, life's molecules interstellar nomads. As 3I divided by Atlas nears solar trial, curiosity mounts. Will heat unveil more anomalies, or confirm it's a galactic fossil? Tail evolutions, green persistence, keep us hooked, each observation peeling layers of mystery, revealing universe's diverse recipes for worlds. As October 30th, 2025 draws near, 3I divided by Atlas hurtles toward its most critical rendezvous yet, perihelion, the point of closest approach to the Sun, at a mere 0.44 astronomical units, roughly 66 million kilometers, placing it inside Mercury's orbit and subjecting it to intense solar radiation that could either illuminate its deepest secrets or shatter it entirely. This pivotal moment, calculated with precision by astronomers at NASA's Jet Propulsion Laboratory using orbital data refined since its July 1st discovery, marks the comet's transformation from a distant speck into a blazing spectacle. Its ice is sublimating at rates that could triple its brightness if it holds together. But here's the catch. From Earth's vantage, 3I divided by Atlas will vanish into the Sun's overwhelming glare starting mid-October, hidden for weeks during its peak activity, leaving scientists in a state of suspended anticipation. What changes will unfold unseen? Will thermal stresses crack its nucleus, exposing volatile layers preserved for billions of years, or will it emerge unscathed, ready for December's scrutiny? This observational blackout stems from basic geometry. Earth's position aligns the comet too closely with the Sun in our sky, less than 10 degrees apart, drowning its light in twilight scatter. Telescopes like Hubble or the James Webb Space Telescope, despite their prowess, can't pierce that veil effectively, forcing reliance on pre-perihelion models and post-emergent surprises. Predictions vary, based on its hyperbolic trajectory, clocking excess speed of about 3.5 kilometers per second. Beyond solar escape velocity, 3I divided by Atlas carries momentum from interstellar origins, I divided by Atlas, based on its hyperbolic trajectory, potentially aiding survival by limiting linger time near the sunday. Yet comets are notoriously unpredictable. Solar heating penetrates meters deep, building gas pressures that can fracture weak structures. Early signs from September's Gemini Observatory images show a coma expanding to 50,000 kilometers wide, with tail lengths reaching 2 million kilometers, indicators of robust outgassing, but also harbingers of instability if jets become asymmetric. Historical precedents fuel the speculation. Take Comet Holmes in 2007, discovered in 1892 but unremarkable until October 23rd, when it erupted in a massive outburst, brightening from magnitude 17 to 2.8. Visible to the naked eye in mere hours, its coma swelling to moon-sized proportions. Astronomers theorized subsurface pockets of amorphous ice crystallizing, releasing trapped gases in a runaway chain reaction. If 3I divided by Atlas follows suit during its hidden phase, we might witness a similar flare upon re-emergence, its brightness surging unpredictably. Or consider the ill-fated comet Ison in 2013. Hyped as the comet of the century, it fragmented hours before perihelion on November 28th, its nucleus disintegrating under solar tides and heat, leaving a ghostly debris trail captured by SOHO spacecraft. Ison's demise, analyzed in detail by NASA's Solar Terrestrial Relations Observatory, revealed how fresh comets, those on first inner system passes, often succumb, their volatile matrices too pristine to withstand the assault. Phys.org's coverage on September 20th, 2025, highlights similar risks for 3I divided by Atlas, noting its interstellar status amplifies uncertainties. Unlike solar system comets acclimated over orbits, this wanderer has slumbered in near absolute zero for eons. Its ice is potentially more brittle from cosmic ray bombardment. The article quotes planetary scientist Quanzi Ye from the University of Maryland, who suggests the comet's high carbon dioxide content detected by Webb could drive early fragmentation, as CO2 sublimes at lower temperatures than water, creating uneven stresses. If it breaks into multiple pieces, each fragment might develop its own coma and tail, turning one object into a scattered fleet, much like Shoemaker-Levy 9's 21 shards that pummeled Jupiter in 1994 after tidal disruption. Guardian reports from September 18th echo this, describing 3I divided by Atlas as a cosmic wildcard whose perihelion could yield unprecedented data on interstellar chemistry if it survives, or a spectacular light show if not. They reference live stream initiatives from observatories like Mauna Kea in Hawaii and La Silla in Chile, where teams plan virtual watch parties using archived data and simulations to bridge the glare gap. Imagine tuning in to a NASA-hosted feed on October 30th, with real-time models animating the comet's solar slingshot, temperatures spiking to 200 Kelvin on the sun-facing side, jets erupting like geysers, propelling dust at kilometers per second. These streams, bolstered by citizen science apps like Comet Watch, encourage users to report post-perihelion sightings starting December 1st, when the comet reappears in the pre-dawn sky at 1.8 astronomical units, 270 million kilometers from Earth, positioned ideally for Southern Hemisphere viewers. The re-emergence window, peaking mid-December, promises optimal conditions, far enough to avoid atmospheric distortion, close enough for detailed spectroscopy, with ground giants like the extremely large telescope under construction in Chile. If intact, 3I divided by Atlas could brighten to magnitude 5, binocular visible, its tail spanning degrees as Earth's orbit shifts viewing angles. But fragmentation scenarios intrigue more. Multiple nuclei could create a strung-out chain, each with unique chemistries revealed by varying outgassing. Borisov, in 2019, offered a preview. Its fragments analyzed by Hubble showed consistent composition. But 3I divided by Atlas's anomalies, like nickel-rich emissions, might vary by depth, exposing layered histories from its parent system's protoplanetary disk. This suspense ties into broader cosmic queries. How do interstellar objects endure such trials after interstellar isolation? Kinematic models from the European Southern Observatory, published in September 2025, estimate 3I divided by Atlas's age at over 7 billion years, linking it to the Milky Way's thick disk, where stars formed amid higher radiation fields, potentially hardening its structure. Yet solar proximity could undo that intense ultraviolet might photodissociate molecules, altering spectra we see post-perihelion. Guardian pieces speculate on organics. If Webb detects complex hydrocarbons during December scans, it bolsters ideas of galactic material exchange, where comets like this seed, planets with life's precursors. Phys.org articles from September 21st detail outburst potentials. If subsurface volatiles ignite, brightness could jump magnitudes, rivaling Venus temporarily. Historical outbursts like Schwarzmann-Wachmann, one's periodic flares every few months due to solar heating, suggest 3I divided by Atlas might exhibit delayed activity, jets continuing weeks after perihelion as heat propagates inward. Live streams could simulate this, using data from SOHO's coronagraphs, which blocks solar light to image nearby objects, potentially catching fragments if disintegration occurs. The curious peaks with survival odds. Preliminary thermal models from Caltech predict 80% integrity, based on its moderate size and velocity, but variables like porosity, how loosely packed its rubble, could tip it. If porous like many comets, gas buildup explodes outward, denser, it weathers the storm. December's views, with the comet at opposition-like geometry, allow radar from Goldstone to map any changes, measuring spin alterations from talking jets. Envision the global watch. Amateur networks like the British Astronomical Association coordinate reports, while pros at Keck Observatory plan marathon sessions. If outbursts occur, social media erupts, with photos greenish coma persisting, perhaps from exotic fluorophores. Guardian op-eds ponder implications. A fragmented 3I divided by Atlas scatters interstellar dust, potentially intersecting Earth's path for meteors years hence, carrying alien isotopes. Phys.org emphasizes educational angles. Virtual reality apps simulate the perihelion dive, letting users fly alongside, feeling the heat build up. This engages, especially as Rubin's ongoing surveys since first light, June 23rd, contextualize it amid other comets, like Swan's recent display. As the date nears, questions swirl. Will solar glare conceal a quiet passage or dramatic end? Re-emergence holds keys intact. It unlocks galactic chemistry. Broken, a debris study. Each possibility deepens our grasp of wandering worlds. keeping the cosmos a realm of endless wonder. Picture yourself in the control room at NASA's Jet Propulsion Laboratory on September 26, 2022, as engineers held their breath while the double asteroid redirection test spacecraft, DART for short, barreled toward the tiny moonlet Dimorphos, orbiting the larger asteroid Didymos some 7 million miles from Earth. This wasn't a drill. It was humanity's first deliberate attempt to alter an asteroid's path, a proof of concept for planetary defense against cosmic threats. At 11.14 kilometers per second, DART slammed into Dimorphos, ejecting a plume of debris visible from telescopes worldwide. The impact shortened the moonlet's orbital period around Didymos by 32 minutes, far exceeding the mission's 7-minute goal, and demonstrated that kinetic deflection works. But recent analyses in 2025 reveal intriguing twists. The collision unleashed a swarm of boulders, some as large as 23 feet across, now orbiting the system like a rocky halo. These findings, published in the Planetary Science Journal on July 7, 2025, suggest that rubble pile asteroids like Dimorphos respond unpredictably, with ejected material amplifying the deflection through a recoil effect, boosting momentum transfer by a factor of 3.6, known as beta. This unexpected bounty of boulders raises questions. Could they become secondary hazards in a real deflection scenario? Or do they enhance our ability to nudge threats away? Fast forward to the European Space Agency's Hera mission, launched on October 7, 2024. Aboard a SpaceX Falcon 9 from Cape Canaveral, Florida. Hera is en route to the Didymos system, set to arrive in December 2026, for a forensic examination of DART's handiwork. Carrying a suite of instruments including cameras, a laser altimeter, and 2 CubeSats Juventas and Milani Hera will map the crater left by DART, measure Dimorphos's mass and density, and probe its internal structure with radar. As of September 2025, Hera has completed initial checkouts and is cruising smoothly, with a Mars flyby planned for March 2025 to observe Deimos en route. The mission's goal? To validate DART's results and refine models for future deflections. Imagine the CubeSats deploying like scouts. Juventas will attempt a landing on Dimorphos using low-frequency radar to peer inside, while Milani scans mineral composition with hyperspectral imaging. What hidden weaknesses or strengths will they uncover in rubble pile asteroids? Could Dimorphos's porous nature, perhaps 50% void space, explain the boulder blitz and beta boost? These missions highlight a glaring vulnerability in our planetary defense arsenal: the sunward blind spot, where asteroids approaching from the sun's direction remain invisible to ground-based telescopes until perilously close. The Chelyabinsk meteor in 2013 exploited this gap, exploding over Russia with no warning, injuring over 1,500. To close it, NASA is advancing the Near-Earth Object Surveyor, NEO Surveyor, a space-based infrared telescope designed to detect heat signatures from stealthy rocks. As of 2025, the spacecraft arrived at the Space Dynamics Laboratory in May for integration, marking a key milestone. Scheduled for launch no earlier than September 2027 on a Falcon 9, with a potential slip to June 2028, NEO Surveyor will park at the Sun-Earth L1 Lagrange point, 1.5 million kilometers sunward, scanning the skies for threats larger than 140 meters city killers capable of regional devastation. Over its 5-year baseline survey, it aims to catalogue 90% of such objects, far surpassing current ground efforts. But what if it spots something inbound with short notice? The mission's infrared eyes could provide weeks or months of lead time. But integration challenges in 2025 raise curious. Will delays push the timeline, leaving us exposed longer? Enter artificial intelligence, the unsung hero transforming asteroid tracking from manual hunts to automated vigilance. In 2024, an AI algorithm sifted through existing telescope data, uncovering over 27,000 overlooked asteroids, as reported in the Astronomical Journal on May 1st. This tool, developed by the Asteroid Institute and Google Cloud, used machine learning to analyze 7.5 million images from the NOIRAB Astrodata Archive, spotting hidden gems in the main belt and beyond. Fast forward to 2025, and AI integrations are accelerating. NASA's Sentry-2 system employs neural networks to predict impact probabilities for near-Earth objects, factoring in non-gravitational forces like the Yarkovsky effect, where sunlight unevenly heats an asteroid, nudging its orbit over time. At the Aerospace Corporation, AI models simulate deflection scenarios, optimizing kinetic impactors by predicting boulder ejections post-dart. Imagine AI sifting petabytes from the Vera C. Rubin Observatory, which began operations in 2025, flagging anomalies in real time. Could it detect a stealthy sunward threat before it's too late? Global coordination amplifies these efforts through the International Asteroid Warning Network, IAWN, a consortium of observatories and agencies sharing data to assess threats. In 2025, IAWN is knee-deep in a simulated impact exercise for the Planetary Defense Conference in May, crafting a hypothetical scenario of an asteroid strike in 2041 to test response protocols. This builds on the 2023 tabletop drill, where participants responded to a fictional 140-meter asteroid impacting near Dallas in 2030. UNOWASA facilitates these via the Space Mission Planning Advisory Group, ensuring seamless info flow from detection to decision-making. For real events like 2025 FA-22's flyby on September 18th, IAWN orchestrated a worldwide observing campaign, rallying telescopes to refine its orbit and characteristics, treating it as a planetary defense dry run. What if the simulation uncovers gaps in international treaties? Could a UN resolution mandate deflection sharing, preventing rogue actions? These threads weave a tapestry of evolving defense. DART's bolder surprise, detailed in IFL Science on July 9, 2025, shows impacts can spawn mini-swarms, complicating trajectories but enhancing push efficiency. HERA's 2026 arrival will quantify this, perhaps revealing Dimorphos's core density via gravity measurements. NEO Surveyor's infrared hunt, budgeted at $1.2 billion, promises to catalogue threats by 2033. But 2025 audits flag hurdles like supply chain delays. AI's role expands open tools. On June 27th notes, NASA's strategy faces challenges, yet AI could streamline detections. IAWN's exercises, like the 2025 conference scenario, simulate multi-nation responses, questioning, how do we communicate risks without panic? Ponder the unknowns. If DART's boulders intersect paths, do they create new hazards? HERA might answer. But until then, simulations tease possibilities. NEO Surveyor's L1 perch could spot sunhiders. But what if it misses a long-period comet? AI algorithms evolve, perhaps predicting Yarkovsky drifts with 99% accuracy by 2030. IAWN's networks grow. Incorporating amateur inputs, could a backyard telescope tip the scales in a crisis? This arsenal builds resilience, yet curious persists. Will the next threat test these tools, or reveal overlooked flaws? As 2025 unfolds, with FA-22's campaign honing skills, humanity edges toward mastery over cosmic roulette. Each advance a step in safeguarding our fragile world. Delve into the heart of the September 2025 cosmic flurry, where a cascade of near-Earth objects from the bus-sized 2025 RJ2 zipping past on September 15th at a hair-raising 0.78 lunar distances, to the skyscraper scale 2025 FA22 sweeping by just 3 days later at 2.2 lunar distances, has astronomers debating whether we're witnessing a statistical fluke or a subtle pattern woven into the commonnance, the fabric of our solar system's rhythms. This surge, as some dub it, isn't isolated. Add in the smaller 2025 BP6, grazing at a mere 9,710 kilometers earlier in the month, and 2025 SY1 following on September 19th at 35,500 miles, and the tally climbs to dozens of close approaches logged by NASA's Center for Near-Earth Object Studies that September alone. But is this clustering mere chance, amplified by our sharpening gaze on the skies, or does it hint at deeper forces synchronizing these ancient drifters? Start with the numbers for context-raw data from the Minor Planet Center, and NASA's databases paint a picture of a busier than usual month. September 2025 saw at least 4 notable flybys within 5 lunar distances. RJ2 at 301,000 kilometers, FA22 at 841,000 kilometers, BP6 at its ultra-close 9,710 kilometers from Earth's center, effectively skimming geosynchronous satellite altitudes, and QV5 on September 3rd at about 500,000 miles. That's not counting the swarm of fainter, smaller objects. Dozens more threaded through our neighborhood, each catalogued by automated systems like the Pan-STAR surveys in Hawaii or the Catalina Sky Survey in Arizona. Statistically, near-Earth objects pass within 0.05 astronomical units, about 7.5 million kilometers every month. But September's density feels amplified, sparking curiosity. Why this particular window in 2025? One compelling explanation lies in observational bias. The idea that we're not seeing more activity, but simply spotting more of what's always been there, thanks to leaps in technology. Enter the Vera C. Rubin Observatory in Chile, which captured its first light images on June 23, 2025, a milestone that unleashed a torrent of discoveries. In its initial 10 hours of operation alone, Rubin netted thousands of new asteroid detections. Its 8.4-meter mirror and massive 3.2 gigapixel camera, re-scanning the sky every few nights with unprecedented depth. This quantum jump in sensitivity, far surpassing older surveys like NEOWISE or Linear, means fainter objects, once lost in the noise, now pop into view. Imagine upgrading from a blurry webcam to a high-definition cinema camera. Suddenly, the background extras become stars. Rubin's first light triumph, detailed in NSF announcements on June 23rd, showcased not just galaxies, but moving dots, asteroids, like those in September's lineup that might have slipped by unnoticed in prior years. So, is the surge real? Or are we just finally tuning in to the solar system's constant hum? Yet, dismissing it as pure bias overlooks subtleties that keep the debate alive. Consider apophenia, that human tendency to spot patterns in random data, like seeing faces in clouds or conspiracies in coincidences. In astronomy, this manifests when clusters like September's trigger speculation. X posts from September 20th buzz with users linking the events to galactic alignments or hidden forces. One thread amassing over 200 replies debating whether solar cycles play a role. Solar activity, peaking in 2025 during Cycle 25's maximum, unleashes flares and coronal mass ejections that could subtly influence detection, perhaps by ionizing the atmosphere and affecting telescope clarity, or even perturbing satellite orbits used for tracking. A strong flare on September 10th, for instance, disrupted radio communications briefly. Could similar events mask or highlight faint asteroids during observations? While physics argues against direct gravitational influence, solar wind is too tenuous to budge rocks. The idea tantalizes. What if heightened solar monitoring in 2025, amid the cycle's peak, coincides with better asteroid spotting, creating an illusory surge? To test this, crunch the stats. Wikipedia's list of asteroid close approaches in 2025, while focusing on tighter encounters, notes BP6's extreme proximity under 1 lunar distance and FA22's as a once-a-decade event. Cross-reference with NASA's monthly updates through September 2025, and the count of objects within 10 lunar distances hits 20 plus, higher than the 2024 average of 15 per month. But zoom out. Over the past decade, detections have climbed 30% annually per IAU reports, driven by surveys like Rubin. If we plot this on a graph, imagine a line chart with years on the x-axis and monthly close approaches on the Y2025's September spike. Aligns with the upward trend, not an outlier. Yet, the temporal bunching 4 in a week defies Poisson distribution expectations for random events, where clusters should occur, but rarely this densely. Probability calculations suggest a 1 in 50 chance for such grouping in a given month, keeping the Y now alive. Add the interstellar wildcard, 3I divided by Atlas's arrival, discovered July 1st with perihelion, October 30th, overlaps suspiciously with the asteroid wave. Could its passage gravitationally shepherd smaller bodies, like a massive ship creating wakes? Physics rebuffs this 3I divided by Atlas's mass, under a few trillion kilograms, exerts negligible pull at millions of kilometers per Newton's inverse square law. Orbital elements confirm no shared history. FA22's elliptical path screams solar system native, while 3I divided by Atlas's hyperbolic eccentricity exceeds 1, unbound and alien. X discussions from September 10th speculate debris trails from 3I divided by Atlas intersecting local asteroids, but spectra differ carbonaceous for FA22, CO2 rich for the comet. Perhaps solar cycles link indirectly. Flares in 2025's maximum could enhance ionospheric disturbances, improving or hindering radar detections, creating perceived clusters. Or consider gravitational resonances. Jupiter's pull synchronizes Apollo group asteroids like FA22 and RJ2 over millennia, potentially bunching encounters every few decades. Historical data from the MPC shows similar spikes in 2015 and 2005, aligning with orbital harmonics. If we graph resonance periods x-axis years, y-axis encounter density, a wave pattern emerges, with 2025 cresting. Apophenia creeps in via media. Forbes, on September 16th, called FA22 a once-a-decade event, amplifying perception of rarity, while clustered reports create echo chambers. X threads from September 20th, with users like @MarkBoweren420 linking to YouTube analyses. Debate surge as observational artifact or sign of galactic awakening. @The Patriot Take on September 10th ties it to market surges, blending unrelated events in pattern seeking. Rubin's influence can't be overstated. First light June 23rd unleashed data floods, with September's detections spiking due to commissioning scans. If graphed pre-Rubin versus post, the jump is stark, suggesting bias dominates. Yet curious lingers. What if solar maximum's geomagnetic storms subtly shift small object paths via charged particle interactions? Unlikely, but models from Los Alamos tease possibilities for dust-sized debris. Ultimately, the surge blends chance, tech, and psychology random processes clustering like lottery wins, amplified by Rubin's eyes. As 2025 data accrues, with Wikipedia lists updating approaches, patterns may clarify or dissolve. Questions persist. Does this foreshadow busier skies, or just our awakening to them? Each new detection keeps the cosmos a puzzle, inviting endless exploration. In the swirling vortex of online forums and late-night podcasts during July 2025, whispers about 3I divided by Atlas quickly escalated into full-throated speculation. Could this interstellar comet, with its unusual green glow and hyperbolic trajectory, be more than a natural wanderer? Perhaps a probe from an advanced civilization, probing our solar system under the guise of cosmic debris. Harvard astrophysicist Avi Loeb, no stranger to bold claims, co-authored a paper that month, framing the object as a potential pedagogical exercise in considering extraterrestrial origins, suggesting its path might allow easy access to Earth if it were engineered tech. The idea ignited imaginations, after all. Why would a rock from beyond our sun exhibit such skewed chemistry, with carbon dioxide ratios far exceeding typical comets, unless it masked something artificial? USA Today ran with the story on July 30th, quoting Loeb on the possibility of hostile alien technology, while social media erupted with theories linking the comet's arrival to unexplained global signals or even government cover-ups. Yet, as tantalizing as these notions are, they crumble under scrutiny, revealing instead how our quest for the extraordinary often overlooks the elegant simplicity of nature's own enigmas. Recall the frenzy around Oumuamua, the first confirmed interstellar object spotted in 2017, a cigar-shaped enigma tumbling through our system with an acceleration that defied easy explanation. Loeb famously hypothesized it might be a light sail or probe from an alien civilization, arguing in a CNN piece from November 6, 2018, that its flat shape and non-gravitational push resembled engineered tech sent to scout Earth. The media latched on, with headlines fueling debates that echoed across platforms like Reddit, where users dissected its oddities as potential evidence of extraterrestrial visitors. But subsequent studies offered grounded alternatives. A University of Chicago paper from April 3, 2023, proposed Oumuamua's acceleration stemmed from hydrogen outgassing, a natural process where trapped gases release unevenly, propelling it like a leaky rocket. No need for aliens, just physics at work, in an object shaped by eons of interstellar erosion. Similarly, for 3I divided by Atlas, Loeb's latest speculation in a Medium post on July 16, 2025, explores if it supports the dark forest hypothesis, where advanced civilizations lurk silently, but NASA swiftly debunked such claims in a Guardian article on September 11, 2025, affirming its natural origins as a comet from beyond our system. This pattern of hype versus reality isn't new. It mirrors the discovery of pulsars in 1967, when Jocelyn Bell Burnell and her team at Cambridge detected rhythmic radio pulses from a source they jokingly labeled LGM-1 for Little Green Men, suspecting an alien beacon due to the signal's uncanny regularity. Space. Com's retrospective on November 28, 2017, recounts how the 1.337-second intervals seemed too precise for nature, sparking brief excitement about extraterrestrial contact. Yet, as more sources emerged, the explanation crystallized. These were rapidly spinning neutron stars, their beams sweeping like lighthouses, a natural phenomenon now known as pulsars, with over 1,000 catalogued today. The University of Cambridge's story highlights Bell Burnell's journey, where initial alien suspicions gave way to groundbreaking astrophysics, earning her the Breakthrough Prize in 2018. Even the iconic Joy Division album cover for Unknown Pleasures immortalizes PSRB 1919 plus 21 signal stack, turning a once mysterious LGM into cultural art. These historical echoes remind us how the unknown often masquerades as the artificial, only to reveal profound natural truths upon closer inspection. For 3, I divided by Atlas. The evidence leans firmly natural, its coma and tail, imaged by Hubble on July 21, 2025, show classic cometary activity, dust and gas ejecting under solar heat, with no anomalous signals or maneuvers suggesting control. Loeb's own paper in Astrobiology acknowledges the need for extraordinary evidence, yet radio scans from facilities like Green Bank Telescope detect only thermal emissions and molecular lines typical of outgassing ices, not modulated beacons. A YouTube video from July 31, 2025, titled Alien Probe or Interstellar Comet? The Real Truth About 3I Divided by Atlas, breaks down these observations, debunking claims with spectral data, showing carbon dioxide dominance as a hallmark of distant formation, not engineering. SYFY's July 29th article explores the what-if of it being a probe, but concludes natural processes suffice. Its trajectory a simple hyperbolic arc shaped by gravity alone. Why the green glow? Likely fluorescence from diatomic carbon or cyanogen, common in comets, though its persistence invites questions about unique molecular blends from its origin system. Media hype plays a pivotal role in inflating these theories, much like the Oumuamua saga, where CNN's 2018 coverage amplified Loeb's ideas, turning a scientific paper into viral sensation. For Borisov in 2019, Scientific American on October 3rd noted its composition mirrored local comets, yet headlines still teased alien possibilities before data settled the debate. With 3I divided by Atlas, Newsweek on July 21, 2025, quoted Loeb on potential alien probes, while Medium posts like Loeb's August 3rd duck test piece speculated on its quacking-like tech, fueling clicks despite natural counter-arguments. Knowable Magazine's February 1st, 2024, piece on interstellar visitors like Oumuamua and Borisov warned of overhype, noting how rarity sparks sensationalism, but subsequent finds suggest they're common. Demystifying the exotic. Space.com's recent article, 5 days ago on September 16, 2025, emphasizes that objects like 3I divided by Atlas are likely ubiquitous, with one potentially always lurking in our system, shifting focus from aliens to galactic abundance. Social media amplifies this echo chamber, where viral conspiracies thrive on platforms like X, formerly Twitter. A search for Oumuamua alien or interstellar object conspiracy since January 1, 2023 yields top posts like one from @NASA Watch on July 29, 2025, debunking Loeb's claims with extraordinary claims require extraordinary evidence still waiting, garnering over 500 likes. Another from @AstroKatie on August 1st mocks the hype. 3I divided by Atlas is a comet, not a spaceship. Let's focus on the real science. With 300 favorites. Conspiracy-leaning threads. Like at Conspiracy Bot's July 31st post, linking 3I divided by Atlas to UFO sightings. Rack up 200 retweets, blending it with unrelated events like recent drone reports. Users like @TruthSeekerX on September 10th speculate, government hiding alien tech in comets, echoing patterns seen in Oumuamua discussions on Reddit. where a June 23, 2023 thread questions Loeb's findings on Pacific spherules as alien artifacts. WGBH's February 5, 2024 interview with Loeb on similar evidence from ocean floors shows how these ideas persist despite skepticism from peers like those in Penn State's AstroWrite blog on July 18, 2023, critiquing Loeb's methods as sensational. The allure stems from psychology. Our brains, wired for pattern recognition, leap to agency in the unknown, as seen in Pulsar LGM jokes, where regularity screamed intelligence before neutron star physics explained it. APS News on February 2006 recounts how over 1,000 pulsars, now known, demystified those signals, turning little green men into a footnote of discovery. For interstellar objects, natural explanations abound. Oumuamua's shape from tidal forces or erosion, Borisov's composition matching local comets, suggesting universal processes. IFL Science, on July 2, 2025, notes 3, I divided, by Atlas's comet-like traits differentiate it from Oumuamua's rockiness, quashing alien hype. The Guardian, on July 3, 2025, reports astronomers viewing it as evidence of common interstellar wanderers, not probes. Nature's July 3 article echoes this, with only 3 such objects acknowledged, but models predict more, normalizing them. A YouTube debunk from August 2, 2025, contrasts claims with data, urging critical thinking. Reddit's April 8, 2024, thread on Oumuamua and Borisov discusses binary star ejections as natural sources, far likelier than tech. Planetary Society's August 6th podcast frames 3I divided by Atlas as a third visitor, emphasizing science over sensationalism. Nye Times, on July 4, 2025, notes its cometary traits align with Borisov, reinforcing natural origins. Why do these theories endure? Media thrives on clicks. Scientific American's 2021 interview with Loeb shows how provocative ideas boost engagement. On X, posts like @UFO Truth Seekers September 15th claim 3I divided by Atlas, green glow equals alien engine, gain traction with 100 favorites, blending fact with fiction. Facebook groups on September 14th discuss its debate about origin, with skeptics stressing natural explanations first. Loeb's Medium on October 9th, 2024, reflects on Oumuamua's pancake shape as mysterious, but UChicago's simple outgassing model counters. In essence, while alien tech captivates, nature's ingenuity forged in stellar crucibles offers richer mysteries. What other natural wonders hide in plain sight, awaiting our unbiased gaze? The cosmos beckons with questions that fuel endless curiosity. As the calendar flips toward late October 2025, astronomers worldwide are bracing for a period of enforced patience with interstellar comet 3I divided by Atlas, whose perihelion passage on the 30th will plunge it into solar obscurity, its most dynamic phase unfolding beyond our direct view until early December. This temporary vanishing act, driven by Earth's orbital alignment placing the comet within 10 degrees of the Sun's disk, creates a blind spot where even powerhouse telescopes like the James Webb Space Telescope struggle against the glare. Yet this hiatus builds suspense. What transformations might occur as solar heat peaks, potentially triggering outbursts that could reveal subsurface volatiles untouched since the comet's ejection from its distant stellar nursery. Models suggest temperatures could climb to 200 Kelvin on its sunward face, sublimating ices at rates that might expose organic compounds or exotic isotopes, offering clues to panspermia theories, where life's building blocks hitch rides across the galaxy. If fragmentation happens, as speculated in X discussions from September 20th, where users debate its pulsing green glow as a harbinger of instability, the reemergence could present not one comet but a fragmented chain, each piece a unique puzzle in interstellar chemistry. Come early December, the viewing geometry shifts favorably as Earth's motion carries us to a vantage, where 3I divided by Atlas reappears in the pre-dawn sky, at a safe 1.8 astronomical units, about 270 million kilometers from our planet. This distance strikes a perfect balance, far enough to minimize atmospheric interference, yet close enough for detailed spectroscopic mapping with ground-based arrays like the Very Large Telescope in Chile or Gemini in Hawaii. Southern Hemisphere observers will have the prime seats, with the comet potentially reaching magnitude 5, binocular visible under dark skies, its tail stretching degrees across constellations like Aquarius. What might we see? If perihelion stresses induced jets, as hinted in pre-discovery images from the Vera C, Rubin Observatory's first light on June 23rd, the tail could display multiple components. Ion streams blue from solar wind and dust trails, yellow from reflected light, each revealing activation phases of different volatiles. Amateur contributions could prove pivotal here. Apps like Stellarium or Sky Safari allow tracking, and networks such as the British Astronomical Association encourage reports of brightness fluctuations, which might indicate ongoing outbursts tied to its nickel-rich emissions. This window extends into 2026, with 3I divided by Atlas remaining accessible for months, as it recedes outbound, its hyperbolic path carrying it back to interstellar voids. By January, northern observers join the hunt as it climbs higher, potentially allowing radar bounces from facilities like Goldstone to measure spin changes or surface alterations post-perihelion. The prolonged visibility, unlike Oumuamua's brief 2017 cameo, invites multi-wavelength campaigns: ultraviolet for gas, ionization, infrared for dust, warmth, and radio for molecular lines that could detect organics like those in Borisov 2019. What if Webb captures amino acids or hydrocarbons? Such finds could redefine our understanding of galactic material exchange, suggesting comets like this routinely seed planets with prebiotic soups. X posts from amateur astronomers, like those on September 20th sharing binocular tips for similar comets, underscore how citizen science might spot subtle evolutions, such as episodic flares, hinting at internal reservoirs awakening after eons in the cold. Meanwhile, Comet C 2025 R2, better known as Swan, discovered on September 11th by Ukrainian amateur Vladimir Bezugli via SOHO's Swan instrument, continues its post-perihelion display into late 2025, its greenish coma and tail potentially lingering for Northern Hemisphere viewers through November. As of September 21st, reports from Earth sky note its magnitude hovering around 6.5. Accessible with binoculars low in the western sky after sunset, near Virgo's Spica and Mars's reddish gleam. If it survives intact, as hoped in Planetary Society guides for spotting it, Earth crossing its orbital plane around October 5th could spark a new meteor shower, Swanids, raining faint streaks from hydrogen-rich fragments. Amateur roles shine here. Databases like the Comet Observation Database welcome magnitude estimates and tail sketches, which could reveal if sublimation jets alter its path unpredictably. A common quirk in fresh Oort cloud visitors. What if outbursts occur? As with Holmes in 2007, such events might brighten it to naked eye levels, turning backyard stargazers into key witnesses of volatile evolution. Shifting to asteroid 99942, Apophis. Preparations for its April 13th, 2029. Flyby closer than geostationary satellites. At 32,000 kilometers are ramping up in 2025, with ESA's Ramses mission proposed for approval at the 2025 Ministerial Council as the next planetary defense venture. NASA's OSIRIS-APEX, repurposed from OSIRIS-REx, is already en route for a June 2029 rendezvous, poised to document tidal-induced changes like spin alterations or landslides during the Earth pass. As of September 2025, University of Maryland teams are advancing mission concepts, including prototype testing for flyby tech, aiming to secure resources by semester's end. Live Science on September 9th notes the event's visibility to billions, potentially magnitude -3, rivaling Venus. But what surface secrets might Ramses' hyperspectral scans reveal? Perhaps water-altered minerals, hinting at ancient hydration. Amateur astronomers could contribute pre-flyby baselines, tracking its faint magnitude 20.3 position in Virgo as of September 21st, using apps for ephemerides to log brightness variations that might signal outgassing. The Vera C. Rubin Observatory, fresh from its June 23rd first light triumph, is revolutionizing surveillance in late 2025, its commissioning phase yielding ever-changing universe snapshots that include asteroid swarms and comet tails. Adler Planetarium's June 27th blog details these images, showcasing distant galaxies alongside moving objects like FA22, raising questions. How many more hidden transients will its every few nights scans uncover by 2026? International collaborations, like those at the NSF-DOE partnership, amplify this, with data shared via NORLab archives for global analysis. Amateurs benefit too. Rubin-inspired citizen projects encourage processing subsets for anomaly detection, potentially spotting new comets or asteroid families. Complementing this, NASA's NEO-Surveyor mission hits a milestone in May 2025, with spacecraft delivery to the Space Dynamics Laboratory for integration, eyeing a September 2027 launch aboard Falcon 9, though delays could push to 2028. Instagram updates from September 17th highlight its infrared telescope's role in hunting sunward blind spot threats. But what unexpected heat signatures might it capture during its 5-year survey? Perhaps dark comets or mini-moons? Before anyone else, systems involvement since 2023 adds layers, with the mission's $1.2 billion budget fueling innovations in asteroid characterization. Collaborative efforts with ESA and amateur networks could integrate NEO-Surveyor data by 2026, creating a global alert system where backyard scopes confirm space-based finds. Amateur astronomers stand as unsung heroes in this era, with tools like the Comet Observation Database logging Swan's greenish tail evolutions through November 2025, potentially revealing fragmentation if jets intensify. Planetary Society guides for spotting Swan emphasize binoculars for its magnitude 6.5 position near Virgo. But what if public reports catch a sudden flare, as with amateur discoveries like Bazoogli's Swan on September 11th? International partnerships shine. UNOSA's Space Mission Planning Advisory Group coordinates data sharing, blending pro and amateur inputs for events like Apophis preparations. X-keyword searches from September 21st reveal enthusiasts sharing viewing tips for Swan, with threads debating its meteor shower potential on October 5th. These windows foster collaboration, with Rubin's petabyte floods analyzed via AI at institutions like UCLA, potentially unveiling new exoplanet links by tying comet chemistries to distant disks. What undiscovered patterns might emerge in 2026 data, perhaps clustering resonances explaining September's surge? NEO-Surveyor's L1 perch, detailed in Utah State University's updates, could spot Venus-hiding asteroids, as warned in recent CZEN articles. Amateur events, like Adler's September 16th lecture on Rubin's first light, engage communities, sparking curiosity. How might your backyard observation contribute to spotting the next interstellar guest? As 2025 fades into 2026, these observational portals from 3i divided by Atlas's December return to Apophyse's looming 2029 Prep Blend Pro-Am synergy, raising curious. Will Rubin's scans reveal a hidden comet swarm? Or Neo-Surveyor's infrared eyes uncover a stealthy threat? Each night sky session holds potential discoveries, keeping the universe a canvas of endless questions. Envision a bustling spaceport in the New Mexico desert by the year 2030, where tourists don sleek pressure suits, not for a suborbital joyride, but for a week-long excursion to a near-Earth asteroid, harvesting samples of ancient rock while orbiting high above the blue marble below. This isn't far-fetched science fiction. Companies like Astroforge and Transastra are already prototyping missions in 2025 to mine NEOs for precious metals and water, turning planetary defense targets into economic frontiers. As Blue Origin and SpaceX expand their fleets, space tourism evolves beyond Virgin Galactic's brief hops. Imagine a Starship variant docking with an asteroid like 2025 FA-22's kin, allowing civilians to conduct microgravity experiments or simply gaze at Earth from a rocky vantage. But what economic ripple effects might this unleash? Could asteroid resources flood markets with platinum, crashing prices and sparking a new industrial revolution? Or ignite international disputes over space mining rights under the Outer Space Treaty? This optimistic vision hinges on a robust planetary defense ecosystem, maturing by the early 2030s, where NASA's Neo-Surveyor, launched in 2027 or 2028 catalogues 90% of city-killer asteroids over 140 meters, closing the sunward blind spot that hid threats like Chelyabinsk, integrated with the Vera C. Rubin Observatory's nightly sky sweeps since its 2025 debut. This network provides decades of lead time for deflections. Picture routine operations. A DART successor, perhaps an upgraded kinetic impactor from ESA's Ramses program, gently nudges a hazardous rock years in advance, turning potential disasters into non-events. The International Asteroid Warning Network, honed through 2025's exercises at the Planetary Defense Conference, coordinates seamlessly, nations sharing data via UN protocols, preventing panic with transparent alerts. In this scenario, impacts become as manageable as hurricanes, with evacuation apps and insurance policies tailored to cosmic risks. But what societal shifts follow? Might this security foster a spacefaring boom, with colonies on the Moon using asteroid-derived water for fuel, extending human reach to Mars by 2040? Interstellar archaeology emerges as a crown jewel in this future, with predictions from 2022 studies in the Planetary Science Journal, estimating the LSST Rubin's Core Survey, detecting up to 15 interstellar objects over its 10-year run, a rate that could climb to 10 or 20 annually as Neo-Surveyor's infrared eyes join the hunt. By 2030, private ventures like those proposed by Astroforge might send probes to these wanderers, sampling chemistries that map galactic evolution, carbon dioxide rich like 3i divided by Atlas, suggesting frigid births around red dwarfs, or organic-laden hinting at panspermia pathways. Posts from space enthusiasts, like at Penst 185, 5 June 10, 2019, quip about space archaeology as the ultimate pursuit. But by 2035, it could be reality. Tourists on orbital hotels analyzing comet fragments via augmented reality, blurring lines between vacation and science. What revelations await? Might these objects carry microbial fossils, proving life ubiquitous? Or exotic isotopes rewriting stellar nucleosynthesis timelines? STEM education thrives in this landscape, Inspired by 2025's events like Rubin's first light and 3I divided by Atlas's passage, programs like ESA's MoonCamp 2025-2026 challenge students to design lunar habitats, fostering skills in 3D modeling and sustainability. With over 5,000 participants globally, by September 2025, NASA's STEM initiatives, such as the Human Exploration Rover Challenge, evolve to include asteroid scenarios where teens build rovers for NEO simulations, igniting passions that lead to careers in space tech. A Time for Science's STEM Expo 2025, held in Greenville, North Carolina, draws over 40 exhibitors with hands-on activities tied to real missions like DART's legacy, inspiring discovery in young minds. By 2030, virtual reality platforms simulate interstellar flybys, letting students visit 3I divided by Atlas-like objects, analyzing data in classrooms worldwide. But how does this inspiration translate? Could it bridge gender gaps in STEM, as seen in ESA's projects engaging diverse groups, or spark innovations like student-designed AI for asteroid tracking? Transition to a more tempered outlook. By 2035, the system faces real tests with city-killers asteroids 100 to 300 meters wide, large enough for regional havoc, but small enough to evade full cataloging, even with NEO Surveyor. Statistical models from the Planetary Defense Conference 2025 predict one such encounter every few decades, prompting hybrid deflections, kinetic impacts combined with nuclear standoff bursts to vaporize surfaces, creating thrust without fragmentation risks. Imagine a scenario where a 200-meter rock is spotted 2 years out. IAWN activates, but political hurdles delay. Nations debate nuclear use under treaties, echoing 2025 simulations, where a hypothetical strike on Dallas tested coordination. Success might avert disaster, but partial failures could scatter debris, causing multiple impacts like a shotgun blast. What ethical dilemmas arise? Prioritizing deflections over populated areas, or the economic fallout from disrupted orbits affecting satellite constellations? Space tourism intersects here too. Private firms like SpaceX might offer defense tours, where paying passengers observe deflection rehearsals from orbit, blending adventure with education. But risks loom. A city-killer near miss could ground flights, as in 2025's FA-22 flyby that briefly heightened alerts. STEM programs adapt, with initiatives like Air and Space STEM Outreach's events inspiring resilience, students modeling nuclear deflections in simulations, pondering fallout scenarios. Could this medium path foster innovation, like AI-driven early warnings, or expose vulnerabilities in global unity? In the starkest visions, by 2040, a long-period comet, 20 kilometers wide, arriving from the Oort cloud with mere months' notice overwhelms defenses, its kinetic energy eclipsing dinosaur-killing Chicxulub. Nuclear barrages might fragment it, but shards could still rain devastation, triggering global winters from dust veils. 2025's conference scenarios simulate this, with participants grappling uncoordinated responses leading to chaos. Space tourism halts, economies crater, but survivors rebuild with hardened outposts, lunar bases stocked from NEO resources, humanity scattering to evade extinction. STEM education pivots to survival tech, inspiring post-apocalypse innovations like biodomes. What legacies endure? A unified species, or fragmented societies vying for orbital refuges? Interstellar detections surge in these futures models, predict trillions adrift in the galaxy, with one always in our system, per National Geographic's July 24, 2025 article on Rubin's potential to spot streams of them. By 2030, private missions rendezvous with these, tourists collecting samples via robotic arms, fueling archaeology that maps stellar ejections. STEM blooms, ESA's 2025-2026 projects like AstroPi engage students in coding for space, inspiring coders who design AI for comet hunts. What if one yields alien tech after all? Are pending scenarios? Or reveals life's universality, reshaping philosophy? These paths, optimistic ecosystems, medium trials, dire reckonings, hinge on 2025's choices. Funding Neo-Surveyor amid delays, fostering IAWN unity, integrating tourism with defense. Space tourism's growth, per Wikipedia's overview, could democratize access, with suborbital flights by 2025, evolving to NEO visits, inspiring STEM through hands-on wonder. NASA's 2025 evaluations of defense strategies emphasize early detection. But what overlooked variables like interstellar comets evading surveys might disrupt? Searches on future space exploration scenarios yield posts like at Pentst 1855's on interstellar archaeology, envisioning it as decent future pursuits, blending legacy with discovery. In optimistic realms, defense becomes routine. Tourism booms, private NEO missions by 2035, per NSS visions, lead to settlements using asteroid water for habitats. STEM inspiration soars. NASA's programs ignite curiosity, with events like Sea Airspace's STEM Expo 2025 empowering youth in aerospace. Medium futures grapple with city killers. Nuclear ethics. Could tourism funds subsidize deflections or create conflicts over resource-rich threats? Dire paths force reinvention. STEM focusing on bioengineering for post-impact survival. What twists await? Interstellar rates, predicted at 1 detectable yearly but potentially more per Arexiv's March 26, 2023 study on LSST, could flood data by 2030, archaeology booming with tourist-backed probes. STEM's role, per Science in Schools September 2nd, 2025, article, inspires through ESA projects, nurturing innovators who might avert catastrophes. Curiosity drives. Will tourism democratize space or exacerbate inequalities? These scenarios beckon exploration, each a thread in humanity's cosmic tapestry. As the crisp autumn winds of 2025 sweep across the globe, carrying whispers of change from distant observatories to bustling city streets, we find ourselves standing at the threshold of a profound awakening, not just to the mechanics of our solar system, but to our intricate role within the vast galactic tapestry. The events unfolding this year, from the unexpected parade of asteroids like 2025, FA22 and its companions, to the enigmatic glow of interstellar Comet 3I divided by Atlas, piercing the veil between stars, serve as more than isolated spectacles. They are harbingers of a deeper truth. Our planet, once perceived as a solitary island adrift in the cosmic ocean, is revealed as a vibrant node in an interconnected web, where materials forged in ancient stellar furnaces constantly exchange hands across light years. This shift in perspective invites us to ponder. If the galaxy is a living, breathing ecosystem of shared elements and energies, what responsibilities does that impose on us as its newest aware inhabitants? Consider the raw elements that compose your very being. The carbon in your cells, the oxygen in your breath, the iron coursing through your veins. These weren't born here on Earth in isolation. They are the recycled remnants of supernovae that exploded billions of years ago, scattered across the Milky Way and reassembled in our sun's nurturing disk. Objects like 3I divided by Atlas, potentially older than our solar system at over 7 billion years, carry echoes of those primordial blasts, their chemistries dominated by carbon dioxide and laced with unusual nickel abundances, hinting at stellar environments far different from our own. As it swings through perihelion on October 30th, hidden from view, and re-emerges in December for extended study, we might decode signatures of the galaxy's thick disk, a relic zone where stars formed amid higher radiation and lower metallicities. What stories could these volatiles tell of early galactic chemistry? Perhaps even the distribution of life's precursors. The curiosity here lies in the unknown. If such wanderers are as common as models suggest, potentially one detectable every year, or more with advancing surveys like the Vera C. Rubin Observatory's ongoing scans, then our system is routinely bathed in extraterrestrial gifts, challenging us to rethink isolation as illusion. This interconnectedness extends beyond mere matter. It binds us to global challenges that mirror the cosmic scale. Take climate change. A terrestrial echo of galactic material flows carbon cycles disrupted by human activity. Much like how interstellar dust clouds seed new stars, the same international cooperation, forging planetary defense networks, as seen in the International Asteroid Warning Network's 2025 exercises, simulating a Dallas impact in 2030, could model unified responses to rising seas or extreme weather. Pandemics, too, parallel unseen cosmic threats. Viruses spreading invisibly, akin to sunward asteroids lurking in blind spots until the last moment. NASA's NEO Surveyor, with its spacecraft integration milestone in May 2025, aims to illuminate those shadows by 2028. But imagine applying similar predictive AI, already sifting Rubin's petabyte floods for asteroid patterns to track viral mutations or climate tipping points. The curious arises. Could the data-sharing frameworks honed for deflecting space rocks accelerate solutions to Earth's crises, turning cosmic vigilance into a blueprint for planetary stewardship? Investment in this vision isn't optional. It's imperative for sustaining our fragile foothold in the universe. The Vera C. Rubin Observatory, having unveiled thousands of asteroids in its first 10 hours post-June 23rd first light, exemplifies how funding transformative tech yields exponential returns not just in detections, but in inspiring generations. Yet budgets fluctuate. NASA's 2025 allocations for planetary defense hover at modest levels, prompting questions: what if we doubled down? Accelerating NEO Surveyor's launch and expanding amateur networks to crowdsource observations? Private sectors like Astroforge, testing asteroid mining prototypes this year, show promise by 2030. Their ventures could yield trillions in resources, subsidizing defense while sparking economic booms. But ethical quandaries loom. Who owns these celestial treasures? The Outer Space Treaty of 1967 prohibits national claims, but as tourism evolves, perhaps with SpaceX offering NEO excursions by 2035, international accords must adapt, preventing a new space race from fracturing unity. Now, let your mind wander to 2050. A horizon where today's curiosities blossom into realities. Interstellar probes, evolved from concepts like Breakthrough Starshot's laser-propelled sails proposed in 2016, could launch fleets toward nearby systems like Alpha Centauri, propelled at 20% light speed, to arrive in 2 decades. By then, data from objects like 3I divided by Atlas, analyzed through AI descendants of today's models, might guide these missions, targeting stars with similar chemical signatures for signs of life. Imagine robotic swarms harvesting interstellar wanderers en route, relaying back organics that confirm panspermia, or even microbial evidence reshaping biology. Space tourism thrives. Orbital hotels host comet chases, where guests in zero-G suites observe flybys via augmented reality, blending leisure with citizen science. Planetary defense? Routine as weather forecasts, AI networks predict and deflect threats autonomously, with nuclear options reserved for rare behemoths. Yet, mysteries persist. What if a probe encounters engineered artifacts, validating Loeb's speculations, or uncovers dark matter influences on galactic flows? This future tantalizes with possibilities, urging us to invest now in the telescopes, missions, and minds that will navigate it. Linking back to 2025's surge, the asteroid clustering, and 3I divided by Atlas's timely visit, these events underscore urgency. If Rubin's scans reveal interstellar objects as commonplace, by 2050 we might catalogue thousands, mapping a galactic highway of debris exchanges. STEM education, already boosted by programs like ESA's MoonCamp 2025-2026, could evolve into immersive simulations, where students pilot virtual deflections or analyze comet spectra, fostering innovators who solve both cosmic and earthly puzzles. Climate parallels deepen. Just as asteroids demand global vigilance, so do emissions. Perhaps asteroid-mined rare earths enable cleaner tech, like advanced batteries for renewables. Pandemics benefit too. AI honed on asteroid tracking could model outbreak spreads, predicting variants with the precision of orbital refinements. The call to action resonates. Sustain funding for surveys like Rubin and NEO-Surveyor, whose delays in 2025 highlight vulnerabilities. Foster collaborations through IAWN, expanding to include private players for hybrid missions. Educate broadly. Integrate cosmic perspectives into curricula, linking galaxy interconnectedness to earthly unity. In 2050, interstellar probes might beam back images of alien worlds, but only if we nurture the curiosity sparked today. What undiscovered connections await? Will mining NEOs unlock sustainable futures, or reveal ethical minefields? These questions keep the flame of inquiry alive, reminding us that in a universe of 400 billion stars, our story is but one thread in an ever-unfolding narrative of connection and discovery. To echo the wisdom of Vera Rubin, the pioneering astronomer whose work unveiled dark matter's invisible hand shaping galaxies, we have peered into a new world and have seen that it is more mysterious and more complex than we had imagined. Her words, spoken in reflection on her groundbreaking discoveries, capture the essence of our current moment, 2025's cosmic events, as portals to that mystery, urging us toward a future where humanity embraces its role as galactic citizens, ever curious, ever vigilant,